Hey everyone, hope you're doing great. In this video, I'm going to talk about a very important aspect of marketing mix modeling, and in particular, Bayesian marketing mix modeling or Bayesian MMMs. This is the concept of priors. Now, priors can be in different forms. The example that you see in front of you in the form of a dummy application, this is using the concept of ROI priors, or you can call them ROAS priors. So, for instance, of course, as you know, marketing mix modeling is a kind of a regression analysis, a very advanced form of it, where you take into account media and non-media variables. So, obviously, for the media channels, you will have ROAS or return on investment, right? ROI. Now, obviously, the objective of the model is to find out uh, through analysis what is the real incremental ROAS or the marginal ROAS of a channel at any given point and at any level of spend. But one of the advantages of the Bayesian analysis is that you can actually start with an initial belief, an initial idea from other sources of truth, because obviously marketing mix modeling is not your only source of truth. By now, I think so much discussion has happened. If you have been following my channel, you would know that I believe in the concept of that triangle, the golden triangle, for instance, what Google also calls it, where you have multi-touch attribution or attribution related data, and also information from other sources like incrementality testing. So from other ground sources or from other sources of truth, you might have some initial belief or idea about what would be the efficiency levels of each channel. Those are the ROI priors. Now, priors can be in other forms as well, but in this particular video, we are only talking about the ROI priors. And I'm going to talk about not just the price, but how to set them and how it actually operates. So in this application in front of you, you see that there are several things happening here. So this line here is very important, that the prior represents your initial belief, the posterior is what you learn after seeing data. With weak data, posteriors stay close to priors. With strong data, they move towards the true ROI. And I think this few sentences here, they just capture the entire essence of this entire concept of priors. So essentially, you have three things in a typical Bayes theorem. You have priors, you have posteriors, and you also have likelihood, which is basically, you can say for the purposes of this video, that it corresponds to the data. So so basically what happens is, there is actually a tug of war that goes on in the Bayesian model between the prior and the data. So and the outcome is the posterior, essentially, and the data, by the way, is like I said, the likelihood. Now, the posterior is what you get, and the posterior will be pulled towards either of these two depending on the relative strength. So if your data is stronger, and we'll just come to in a moment to what I mean by stronger, then it's going to be pulled towards the data. Meaning, suppose your data is distributed, suppose let's consider all normal distributions. Then if your data is distributed, suppose has a distribution, is a normal distribution with a mean at say 5, and your prior beliefs was that the ROAS is actually, and the distribution of that is with a mean of say 3, um, and depending on the standard deviation, depending on how wide the confidence interval is, you would understand whether or not the data is stronger or the prior is stronger, and the posterior distribution will actually move closer to the one which is stronger. But also this depends on the model, so the modeling also will have an impact on it. But this is just to give you an idea how prior and the data work together. So you'll see that the data strength here, so this of course not, this is not exactly how the models work, but this is just to illustrate how it is working in the back end. Like the net effect of it is like that, whether or not it is going to get pulled towards the data or the prior. So that's something that's derived from the model. Okay, that's a property of the modeling aspect of it, which will decide whether or not to give more importance to the prior, or to the data. But suppose, I mean, in some cases you might have very strong priors, and the data might not be, like there may not be enough data points. So yeah, there's going to be the possibility that it's going to be pulled towards the prior. So If you look at the sliders here, and if you look at the distribution, so as you can see, this blue one is the prior distribution, the distribution of ROAS beliefs basically, and they are kind of centered around, if you look at the prior distribution here, yeah, so that's kind of centered around 1.5. Yeah, there you go. And this one's centered around, I think, around 2.15. That's the posterior. And this posterior, this orange one, is a result of the interaction with data and your priors. So your data strength is currently 50%. Your prior strength is a prior ROI mean. This is something that you provide, that you can. So for instance, in Google's Meridian MMM, you can actually provide this. You can provide this ROI per channel, and you can see that this is for paid search here. This particular dummy example shows you. I'll show you for another one channel at least, and you can change that. You can also change the uncertainty level, or the confidence interval, or you can say the standard deviation. In this case, the standard deviation of the prior distribution, that will also sort of change the distribution shape. And you'll see that the ground truth is in this case, of course, known. That's the whole point. So we know that it's 2.8, and you'll see that for the different channels now. So for, obviously, for this is for search, and for the others it's actually taking in dummy value, okay, the distribution of ROI. So you'll see that paid search is 1.5, for the, that's the ROI belief, and the ground truth is actually 2.8, and the posterior is believing it to be 2.5. So basically it's basically under evaluating or under attributing to paid search currently. In case of social media, in case of display, for instance, and in TV, it's actually the ROI belief as well as the posterior distribution is overestimating the effect of the true ROI. Now if we change it, for instance, now suppose we change it, in this case, suppose we change the prior ROI to 2.8, we increase it to 2.8. Let me actually show you the exact case here. So if we make it 2.8, so it's 2.9. You see that as I bring it closer to 2.8, which is the ground truth, all three start getting aligned. This is actually not going to be the case, of course. And first of all, we never know the exact ground truth. There's no such thing as precise ground truth, um, but yeah, it gets pretty close. So you'll see now what has happened, that these two distributions actually have the same mean, which is 2.8, right? The standard deviations differ, of course, which is why the distributions look different. So for instance, if I decrease the uncertainty, the standard deviation of the prior distribution, you'll see that this is how it's looking like, right? And if I reduce it further, it might actually start looking like even more like the posterior distribution in this case, if I'm not wrong. You'll see that's what's happening. They're kind of starting to look much similar now. And so that's yeah, but both of them are still centered around 2.8. And you'll see that these three bars are at the same level, right, in this app. That's how this app is showing, because yeah, the expected revenue by channel, by, and also the ROI for each channel, the three bars for the prior, posterior, and the true ROI are the same. So this gives you a nice intuitive understanding. Like you can play around with this if you want. I'll share the link as well. And I suppose I can just reduce it here, and I reduce the ROI priors, and you'll see the data strength still remains 50%. And you'll see that this time it kind of shifts away, because the prior is weaker, and the prior is lower rather, and you'll see that it's 2.3, and the posterior is 2.55. So basically it's learning from the prior, but it's also learning from the data, right? And therefore, with 50% data strength, you have both prior and data influencing the posterior. But suppose I increase the strength of the data, let's say from 50% to 64%. Let's see what happens then. In this case, you see what's happening is it's 2.62, because it's learning more from the data. When it was 50%, it was 2.55, because it was lesser less closer to the ground truth, because it was learning more from the prior in that case. But in this case, the strength of the data is more, so which is why it's learning more from the data itself, rather than, even though the prior is 2.3. Now if your data strength becomes even more, suppose close to 80%, it becomes even closer, right? So you'll see the distributions look very different now, because the prior distribution is has a completely different mean, far different, like 2.2, I think, 2.3, and this one has a mean, the posterior has a mean of 2.7, which is much closer to the ground truth. This one's not marked here, but from the bars you can see. Now you see that the prior is much more different, and then the posterior is actually much closer to the ground truth. So this depends. So basically what it means is that either you can start with a very good understanding from other ground sources of truth as to what could be the potential real efficiencies of the different channels involved, or you can start with very strong data which follows all the good guidelines. um, and for marketing mix model, I've discussed those elsewhere. So if you follow those guidelines of really good data, you have enough, like number of rows is much greater than the number of predictors, for instance, or regressors. That's one requirement. You have data which is very clean, and not too many missing values, and consistency in data, not sparse data. So there are so many aspects to it, not as many outliers. So all of these things contribute towards data strength, and they have enough variance as well, and coefficient of variation has to be taken into account as well, like how much the variance varies with respect to the mean, um, the ratio the same, and so these different things, like if is there enough variance at all in the data with respect to the revenue, to the in the input variables with respect to the revenue, or vice versa. These things will ultimately contribute to whether or not you have a decent data strength. I can show you another final example of this process in action. This is how it actually looks like. So you can see that in this case also, the difference between, suppose, a weak prior and a strong prior, you'll see that it's varying by the parameter theta, and see that prior, likelihood, and posterior. So likelihood, like I was saying, so that's basically that corresponds to the data. And you'll see how in case of a weak prior, and by weak prior is simply meant that the uncertainty level is much higher. As you can see, the standard deviation is much higher in this case. And you'll see that in this case, the final conclusion after all the data points have been considered in the data set, n equal to 20, it almost, the posterior distribution almost overlaps with the likelihood, with the data distribution. But in this case, where there's a stronger prior, you'll see that the standard deviation is much lesser. The confidence, the intervals, I mean, it's much narrower than this one. The tails are much closer. You'll see that it's a much more bell-shaped curve. You will see that there's still a gap, a delta, even when all the data points have been considered in this example, between the posterior and the data distributions. And if I were to actually run this animation here for you, I hope you can see this, and you'll see nicely it shows that same thing, like how as the data points gather, um, the distributions actually converge. Like in this case, they converge almost neatly and perfectly, because the prior is weaker. But in the stronger case, you'll see that it is actually pulling towards it, and that's the problem. By stronger prior means that if you're, like, your standard deviation is low, but if your belief is wrong, like in this case, the data actually is completely different. You can see it's very different. The mean is somewhere around maybe more than 60, and the prior has a mean of around 40. But because it's a stronger belief, it's a stronger prior, it's actually still pulling the ultimate outcome of this distribution, the posterior, closer towards it. And with a delta remains with respect to the posterior, with respect to the likelihood of the data distribution even after that. So this is a problem. So you need to start with good priors, and it's not good enough to have strong priors, and it needs to be good priors, which should come from very good, um, which should come from really very good sources of truth. Like, you should have good reasons to choose those priors in the first place. So hope this was useful. This was the whole idea. This is what I wanted to show, how Bayesian priors really work and why they're so useful. They're incredibly intuitive, but they're like any weapons. They're powerful, but you would have to use them responsibly and in the right fashion. So yeah, I hope this was useful. If you have any further questions, do let me know in the comments. Thanks for watching, and I'll see you in the next one.